Welcome back. We are going to be going over the next module, and the next module is the structure of atoms and periodic trends. This particular section has these subsections of the Pauli exclusion principle, atomic subshell energies, and electron assignments. Electron configurations of atoms, electron configurations of ions, atomic properties and periodic trends and chemical properties. And this is kind of the rub of the whole thing right here. Ultimately, all of this leads to periodic trends and chemical properties. It's the electron configuration of atoms that gives the atoms their chemical properties. Okay, so let's take a look here at the first subsection, the Pauli exclusion principle. The goals are to recognize that each electron in an atom has a different set of the four quantum numbers, N, L, M sub L, and M sub S. And we're going to learn the names of these in a little bit. And we want to understand the Pauli exclusion principle that no atomic orbital can be assigned more than 2 electrons, and the 2 electrons in an orbital must have opposite spins, different values of M sub S. So let's look at the Pauli exclusion principle here. First, we're going to look at that no 2 electrons in an atom can have the same set of quantum numbers. So we have these 4 quantum numbers for Schrodinger's wave equation. N is the principal quantum number. L is the orbital angular momentum quantum number. M sub L is the magnetic quantum number. And M sub S is the electron spin quantum number. So we've been introduced to these already. And when we use these quantum numbers and we're using the wave equation, we assign numerical values to each of these different types of variables. But you can only have specific numbers assigned to those variables. So for instance, for N, it has to be a 1 or a 2 or a 3 or a 4 or 5 or 6 or 7. L depends on N. L can be 0, 1, all the way up to N minus 1. So for instance, if N is 3, L can be 0, 1, or 2, but it cannot be 3 because L has to be 1 less than N at a minimum. And M sub L is also assigned numbers based on L. So if L is 0, M sub L can only be 0. If L is 1, M sub L can be 0 or plus or minus 1. And if L is 2, M sub L can be 0, plus or minus 1, or plus or minus 2. And M sub S is the electron spin, and you either have a plus 1/2 or a minus 1/2. And roughly speaking, this gives you the shell, this gives you the subshell, but L also gives you the orbital type. So I want you to recall that if L is 0, it's an S subshell with S orbitals. If L is 1, you have a P subshell with P orbitals. If L is 2, you have a D subshell with D orbitals. And if L is 3, you have an F subshell with F orbitals. So L gives you the subshell and the orbital type. And M sub L, these just give you the orientation of the orbitals. So if we go back to L being 1, M sub L can be 0, plus 1, or minus 1. If M sub L is 0, that's a particular orientation. If M sub L is minus 1, that's a different orientation. And if M sub L is plus 1, it's a different orientation altogether. So for 0, plus 1, and minus 1, you have 3 orientations of orbitals. And M sub L, these are numbers assigned to actual electrons within an orbital. So if you have a full set of 4 quantum numbers, you are describing 1 electron. Again, if you have a full set of 4 quantum numbers, you're describing 1 electron in an atom. So the Pauli exclusion principle says you can't have 2 electrons in an atom with the same set. So if you have a 1, 0, 0 plus 1/2, you cannot have another electron with a 1, 0, 0 plus 1/2. But you can have one with a 1, 0, 0 minus 1/2. Okay. So how is this used for the electron configuration of atoms? Well, here we're going to be looking at the electron configuration of atoms based on their quantum numbers, which you can see is set right here. And we're going to start off very easy. We're going to look at the electron configuration for the ground state. So that's the most stable set of electrons you can have on an atom. And when you look at the stability of where that electron could be, the first thing you look at is the shell. The lower the number of the shell, the more stable the electron. And remember, the lower the number of the shell, the closer it is on average to the nucleus. So electrons closer to the nucleus are more stable than electrons farther away from the nucleus. Now, this is interesting because when we look at L really doesn't tell us a whole lot about the distance from the nucleus because it really depends on N. But here we find that zeros are more stable than ones, more stable than twos, and more stable than threes. And remember, we give these letter designations of S, P, D, and F. So here, when we say S, P, D, F, what I'm really talking about is if we look at, say, the fourth shell, which has a 4s and a 4p and a 4d and a 4f, an electron in the 4s is more stable than an electron in the 4p, which is more stable than a 4d, which is more stable than a 4f. We'll learn why these are different, even though they're all in the same shell. For the M sub L, for the different M sub Ls, for a particular L, those energies are all the same. And pretty much for the M sub S, those energies are the same, or the stabilities are the same. So if we look at an H atom with a 1 electron atom, the electron is in the first shell because it's the most stable. And in the first shell, there's only an S subshell, so it's in an S subshell. And the S subshell happens to have one S orbital, so it's in an S orbital. So for the first electron, we like to assign its quantum numbers as 1 for the first shell, 0 for an S subshell, 0 because L is 0 and M sub L can only be 0. And for the first electron, we assign it as a plus 1/2. That is the common way of doing things. You use the plus 1/2 before you use the minus 1/2. Now, when we write the electron configuration of the hydrogen atom, here are two quick ways of doing this. This is called the SPDF format, where you see this 1s2, and 1 here stands for the shell, S stands for the subshell, and this 1 says there's 1 electron in that subshell. Here, this is another way of doing it. It's called the orbital box diagram. And here, instead of just seeing the subshell, you actually see the orbital. So this is a 1s subshell with 1 orbital in it. Every box is an orbital. The 1s subshell only has 1 orbital, so that's what you see. And notice the electron is drawn as an arrow going up, because for the plus 1/2, you draw an arrow up, and the minus 1/2, you draw an arrow going down. Okay. So writing electron configurations, a closer look. So these are things that I kind of explained to you just a moment ago, but we're going to look at them again. For the SPDF format, you start off with the most stable subshell, and you write the shell number and the subshell type, and then the number of electrons in that subshell. So this is 1s1 for hydrogen. For the orbital box diagram, you draw a box for an orbital. So here we have 1 orbital, which is in a 1s subshell. And sometimes they will draw this as just a line instead of a box because it's just easier to do. So this is a 1s orbital also. And here for the hydrogen atom, you would actually put 1 electron in there like this. And that means M sub S is plus 1/2. Now, remember, the Pauli exclusion principle says no 2 electrons in an atom can have the same set of quantum numbers. So let's say we were going to put another electron in here. we could not put another arrow going up because that would mean you'd have a 1, 0, 0 plus 1/2 and another 1, 0, 0 plus 1/2. But you can put an arrow going down because then you would have a 1, 0, 0 minus 1/2. And so when we say with the Pauli exclusion principle tells you that you've got to have a unique set of quantum numbers for every electron in an atom, one of the results of that is that you can only have 2 electrons in an orbital, and that's it. You can have 0, 1, or 2. You can't have 3. So that's part of the fallout of the Pauli exclusion principle, 2 electrons maximum per orbital. And one is up and one is down. So usually we say spin up and spin down because this is the spin quantum number, more specifically the electron spin quantum number. Okay, the next section here is going to be atomic subshell energies and electron assignments. So we're done with the first section of this particular part.